Hello, hi, welcome to the session. In the last session, we had a discussion about methods of generation, and we have discussed about stationary induced EMF method of stationary induced EMF also. And right, okay. Now I think we did one problem. It seems. Now in this session, we will try to find out the polarity of induced EMF, and then we'll move on. Ahead. Okay, so according to the Faraday's laws of electromagnetic induction, that is stationary induced EMF, the rate of change of flux linkages are proportional to induced EMF. The rate of change of flux linkages are proportional to induced EMF. You see, I have a time varying magnetic field. If this is a time varying magnetic field, if this time varying magnetic field linking with another coil and EMF is induced, this induced EMF is going to be measured in the galvanometer. When the flux lines directions are going to change, EMF polarity also going to change, and the galvanometer deflection also going to be changed, maybe forward direction, reverse direction. Okay, so here the polarity of induced EMF, how do you find the polarity of induced EMF? Polarity of induced EMF can be calculated, polarity of EMF can be found, polarity of EMF can be found by Lenz's law and right hand thumb rule. Okay, here the right hand thumb rule for the circular conductor is reverse, be careful. For straight conductor, thumb indicates current direction, closed fingers will indicate flux direction, but for circular conductor quite opposite, thumb indicates flux, closed fingers will indicate current direction. Okay, so let us see the polarity of induced EMF. I have a coil connected with a bulb and galvanometer. We did not connect any source here. That means what, coil is simply a passive element, and right, so it is connected to a bulb and galvanometer. Okay, now near to the coil what I am doing is I am bringing the bar magnet near to the coil. When I am bringing the bar magnet near to the coil, what is happening? Definitely when the bar magnet is here, flux linkages with the coil is 0. When the bar magnet I am bringing closer to the coil, the flux linkages will increase. Because of increment in flux lines, let us assume this as phi1, because of increment in flux lines, here because of increment in flux lines, an EMF is going to be increases or induces, definitely. An EMF is going to be induces. Now we have to find out the polarity of induced EMF. To find the polarity of induced EMF, you have to apply Lenz's law. What Lenz's law says that? Lenz's law says that whenever an EMF induces in a coil or a conductor, that EMF always opposes the very cause of its production. The cause for the production of EMF is increasing change. So it has to oppose increasing change. EMF is a electric quantity. Increment this flux linkages is a magnetic field. So electric quantity, magnetic quantity cannot be opposed. So electric quantity has to drive an electric current. This EMF has to drive an electric current and it has to produce a magnetic field counter to this one. So the EMF will drive the current in the coil and produces a counter flux and produces a counter flux in opposite to the phi1 or very cause of its production. The cause for the production of EMF is what? Phi1. So in order to counter this, phi2 is producing. E2 is producing the phi2. How? E2 has to drive a current. In which direction? We have to find. Apply Fleming's what I can say. Apply Fleming's right hand rule. Simply right hand thumb rule. If you apply right hand thumb rule, here this side is the the coil is placed like this. The coil is placed like this. If you want me to show you, the coil is placed like this actually. Like this. The coil is placed like this. Okay. So these are the coil terminals. So this coil is like this. Now, if you are expecting an EMF, if the EMF is induced and if you are expecting a counter flux, the current has to flow in which direction you need to find out. To find the direction of current, I am applying right hand thumb rule. So okay, so here let us assume the flux is produced from right to left. If you are expecting from right to left, how should be the current direction? Here, how should be the current direction if you are expecting the flux from right to left? If you are expecting that like this, then current has to flow like this. From front side, it has to go upward, downward, upward, downward. It has to go upward, downward. So this is the current entering terminal and this is the current leaving terminal. Okay, this will be the current leaving terminal and this will be the current entering terminal. Alright, the current leaving terminal is going to be the positive terminal here. The current entering terminal is going to be negative terminal here. Why? Because it is not a passive element. The coil is acting like a active element now. It is capable to deliver the current because of EMF. In the coil, EMF is generated, so it is capable to deliver the current. So whatever the current, whatever the terminal, from where, through which terminal, or otherwise from where the current leaves, from where the current leaves, that terminal is called as, taken as positive terminal. In an active element, the current leaves from positive terminal, so that is the reason why I have taken this as a positive terminal. So this is the polarity of induced EMF across the coil. You see here, I am bringing the north pole close to the coil. If I am bringing the north pole close to the coil, the flux line is emitting here. If the flux line is emitting from this coil side is acting like a north pole. When north pole is coming closer, when north pole of bar magnet is coming closer, a north pole is created, and this is how flux lines are going to be opposed. Lens law is going to be obeyed or satisfied. Now let us see, if I move the bar magnet away from the coil, if I take up the coil here, like this, okay, of course, there is a connection, maybe a galvanometer or otherwise a bulb. I am just showing a galvanometer. Now I am moving the bar magnet away from the coil, So if I move the bar magnet away from the coil, what is going to happen here? Flux linkages with respect to the conductor, are going to decrease. There is a change in linkage of flux lines with respect to conductor. When the bar magnet is here, maximum linkages. Here, linkage of flux lines decreases. Here, linkage of flux lines decreases. So definitely an EMF is going to be induced in this conductor. Now this EMF has to oppose the very cause of its production. The cause for the production of EMF is decreasing flux. That means what? North pole is moving away. In order to oppose the decreasing flux lines, and in order to oppose the north pole movement towards the left side, what it has to do? It has to produce a flux line. In which direction? It has to produce a flux lines in this direction. Why? If it can produce a south pole on this side, then this north and south can be attracted. So it can stop the north pole movement away from the coil. Now this will behave like a north pole. Please try to understand here. The reason for the production of EMF is what? Decrease in flux lines. Decreasing flux line is due to north pole is moving away from the coil. In order to oppose that north pole movement, it has to be south pole, so that it can pull towards this one, or otherwise it can oppose the movement of north pole towards the left side. Now if you are expecting the south pole here, north pole here, that means what? Here the flux is producing towards this side, left to right. Therefore, how will be the current direction now? The current direction will be like this. Okay, it has to enter like this and it has to like this. So in the backward, on the back side of the coil, the current go upward. On the front side of the coil, the current go downward. If I represent the current direction here, the current will be downward in the front side of the coil. Now the current leaves from this terminal and current enters at this terminal. The current leaving terminal will be the positive terminal because the coil is acting like a active element. And the current entering terminal will be negative terminal. So this is the polarity of induced EMF. As the flux linkages are changing, definitely that EMF has to oppose that change. EMF is because of change in linkage of flux lines. Whether it is increasing change or decreasing change, definitely EMF induces, and EMF has to oppose the very cause of its production. That is what Lenz's law, and this is how you can find out the polarity of induced EMF. Let me show you in another way, if it is possible. You see here the same example. If I am bringing the north pole here, this pole side should be north pole to oppose the increment in north pole flux lines. Okay. Now if I move the north pole away, then this side has to be south pole in order to oppose the very cause of its production. Okay. All right. So see, let us move on. You see here, there is one more point. I have a time varying magnetic field and I have an induced EMF also. You see the magnetic field variation. The magnetic field variation here, it is constant. Because of constant flux lines, EMF is 0. Why EMF is 0? Because this may be 1 Weber flux lines. 1 Weber flux lines initially 0 flux lines, later 1 Weber flux line. That when the flux is changing from 0 to 1, that 1 Weber flux lines might be attracted, might be attracting or repelling the 1000 number of electrons in the conductor. Now if the 1 Weber flux lines is maintained for 2 seconds or 3 seconds, then nothing. So till 2 seconds the EMF is already the 1 Weber flux lines have attracted 1000 electrons. Now till 2 seconds the flux line is not going to create any force, any neighboring electron, other electrons. EMF is 0. The electromotive force is going to be 0 after some time, because the ability of the flux line is already finished. The ability of flux lines is to attract 1000 electrons. It has already attracted 1000 electrons, created force, and the force is, after some time the force becomes 0. That after some time the force or electromotive force becomes 0. That means what? It will not create a force on the other electrons remaining. Apart from 1000 electrons, it is not going to create or attract or repel any force on the other electrons. Okay. Now you see, as the flux is increasing, as the flux is changing, the EMF is inducing. When the flux is constant, again the EMF is 0. When the flux is decreasing, again the EMF is inducing. So please see that for a constant flux lines EMF is 0. When there is no change in flux lines, EMF is 0. This change in flux lines d phi by dt is because of, it can be due to DC nature. It can be due to DC nature current. DC nature current. That means what? The EMF induction is absolutely 0 for constant flux lines. If you are expecting EMF, there should be continuous change in flux lines. Okay, right. So this is anyhow, we have a circular conductor, and this is flux variation. The flux variation can be increasing, decreasing like this. Now due to this increment, decrement, EMF increases. Wherever the flux is constant, EMF is 0. Okay, let me take up the same example and let me show you in the same manner. Before that, I just wanted to tell you a small question so far we have discussed about. The statement is given like this: in all cases of electromagnetic induction, an induced voltage will cause a current flow in a closed circuit. In such a direction that the magnetic field which is caused by that current will oppose the change that produces the current. If you think that this is going to be somewhat little complex, you see here, that is what we have discussed. You see, the magnetic field produced by the EMF is opposing the very cause of its production. Okay, all right. So this is what, statement of Lenz's law. What is this? The original statement is of the it is a statement of Lenz's law. Okay, it is the original statement of Lenz's law. Okay, let me show you a Lenz's law in a different manner, in another way also. I have a time varying magnetic field. Let me take up a time varying magnetic field here. Phi of t. How do you get phi of t? I will be getting phi of t due to I of t. Let me take up the instance 0, 1, 2, 3 and 4. 0 to 1 the flux is increasing. 1 to 2 the flux is decreasing. Okay. Now I am taking here a circular conductor. All right. Now let me show you outer layer also. Okay. Maybe it is coming, very outer layer is coming like this, but let me, okay, roughly let us take up like this. I have a circular conductor like this. Now on to the circular conductor. In the circular conductor, supply current is flowing, and due to this supply current, a flux is producing. I am assuming 1 to 2. The current is increasing, therefore the flux is also increasing. Let me take 1 to 2, or let me take up 0 to 1. Okay, let me take up 0 to 1. In 0 to 1 duration, the flux is increasing. The flux is increasing. As it is positive half cycle, I am taking the flux upward direction. I am just considering the flux in the upward direction. Okay. So here at 0 instant the flux linkages with respect to conductor is 0. Now as the time changes, the flux linkages are increasing. And of course they are in upward direction. These are increasing flux. These are increasing flux lines. There is a change, na? So initially 0. Now later after some time maybe 1 flux, 2 flux, 3 flux, 4 flux, like that. Flux linkages are with respect to conductor are increasing. Therefore definitely an EMF induces. In the conductor. Alright. Now this EMF has to oppose the increasing change. The reason for the production of EMF is increasing change in flux linkages. In order to oppose the increasing change, the EMF will drive a current and produces a flux lines. How? In the downward direction of flux. Okay. So these are the flux lines due to induced EMF. In order to produce the flux lines in the downward direction, what must be the current direction in the circular conductor? If you are expecting a downward direction of flux lines, the current in the circular conductor must be clockwise. Okay, so this EMF has to drive the current in the clockwise. If the EMF is driving the current in clockwise, that means what? Inside the conductor, the electrons are going to be in this direction. Quite opposite to current direction, na? Okay. Not so many electrons, not all the electrons will not move. Whatever the capacity is there for these flux lines, only those, according to those flux lines, electrons will move. Okay, if the induced EMF current is like this, counter current is like this, counter flux is like this, can you tell me how will be the supply current? The supply current, this is the flux due to supply current only, na? Increasing flux is due to supply current. If you are expecting direction of flux in the upward direction, the current direction must be anti-clockwise. So here, inside in the conductor, the supply current must be in this anti-clockwise direction. So how it is? The supply current is increasing 0 to 1. During 0 to 1 the current is increasing, therefore flux is increasing. As the flux is increasing, EMF is inducing. Now the EMF starts opposing the very cause of its production. How? By driving a counter current to the supply current, by producing a counter flux to the supply flux lines. This is how Lenz's law is going to be satisfied. Okay, this is how Lenz's law is going to be satisfied. You see, if the supply current is in anti-clockwise direction, what will be the electron movement due to that current? The electron movement due to that current will be in clockwise direction. You see, opposite direction. Okay, supply current is driving the electrons in anti-clockwise direction. EMF current is driving in clockwise direction, driving the electrons in clockwise direction. So the net amount of electrons are going to be minimized. And hence the net current flow through the conductor is going to be limited. It will not tend to infinity. Therefore, the system is going to be the system is going to be stable. The system will be smoothly operated. If Lenz's law doesn't satisfy, that means what? If the EMF cannot counter the very cause of its production, if EMF fails to counter the very cause of its production, if EMF is not there, counter current is not there. If counter current is not there, the yellow anti-clockwise direction of flux lines, anti-clockwise direction of electrons will not be there. That means what? There is no counter current to the clockwise direction of electrons. That means as a supply, whenever you give the supply, the supply current increases, the supply flux increases, the supply current keep on increases, to say exactly. The supply current keep on increases. That means what? As the supply current increases, this electron will collide with the neighboring electron and moves the other electron. Those electrons will collide with the neighboring electrons, moves other electrons. That is how multiple number of electrons are going to be energized and they tries to move. Crores of electrons and tries to move here. Crores of electrons tries to move. Why? Because there is no counter. If crores of electrons are moving through the conductor, then that is where spark starts. Jump in electron starts. and that is where sparking in the machine starts, the sparking in the system starts, and the system leads to failure finally. If Lenz's law is not satisfied, system existence is not possible. For every action, there should be an opposite reaction. Then only system can exist. If somebody is slapping continuously, how can I oppose? How can I simply bear it? I should start opposing, or otherwise I should escape. Otherwise, I cannot survive, na? Otherwise, I cannot survive. So, in the same way, EMF has to oppose the very cause of its production. Otherwise, system cannot survive. You see for the second duration, that is 1 to 2, if the flux is decreasing, 1 to 2, if the flux is decreasing. Now, the same, let me take up the same circular conductor. Okay, now the duration is 1 to 2, the flux line is decreasing, it is decreasing flux lines, but still it is positive half cycle only. Positive half cycle means I am not going to change the direction of flux lines. Still it is upward. The direction is going to be upward only. So, but here the flux lines are decreasing now. The amount of flux lines, it becomes, earlier I have got 5, now 5 will become 4, 4 will become 3, 3 will become 2, 2 will become 1 and 0. Okay. So, it will become 5, 4, 3, 2, 0 like that. As the flux lines are decreasing, there is a change in linkage of flux lines with respect to conductor. Yes or no? 5 flux lines, now 4 flux lines linkages with my cheek, 3 flux lines, 2 flux lines. Okay, this is how, whenever the fingers are hitting my cheek, definitely I will get pain. Whether it is increasing change, whether it is decreasing change, or decreasing change, definitely we will get pain now. Okay, when 5 flux lines, when 5 fingers are linking, 4 fingers are linking, 3 fingers are linking, 2 fingers are linking, definitely you will get pain. Whether it is increasing or decreasing. So, here also EMF induces. Now, EMF induces in this. This EMF has to oppose the very cause of its production. The cause for the production is decreasing flux. So, in order to oppose a decrease in flux, this EMF will drive a current and produce a flux in the upward direction. And if it produces a flux in the upward direction, this phi E is supporting this white flux lines or supply flux lines. How it is supporting? It is not allowing the decrement. Actually, it wants to decrease, but EMF is driving a current and producing a flux line, one more flux line in addition to the overall. If one flux reduces, it is adding one more flux. If 2 flux lines are reduces, it is adding 2 more flux lines. In order to get upward direction of flux lines, what must be the current direction? Okay, if you apply right hand thumb rule, to get the phi E in upward direction, the current direction must be anti-clockwise. So, this has to drive the current, the EMF has to drive the current in anti-clockwise direction. How is the supply current? The supply current is also positive but decreasing, na? Positive but decreasing. You look at the supply current here. Supply current is still in the anti-clockwise direction, but it is from 1 to 2. 1 to 2, it is decreasing. As the supply current is decreasing, supply voltage is decreasing, as the supply current is decreasing, this supply current decrement is not allowed by the EMF. How? You see, the current driven by EMF is adding with respect to supply current. If the magnitude of supply current is decreasing from 5 amperes to 4 amperes, now it is adding some more current. If it is decreasing from 4 amperes to 3 amperes, it is adding some more current. And that is how Lenz's law is going to be satisfied. You know already here, this supply current is going to move the electrons in clockwise direction, and whereas the stationary induced EMF or this induced EMF is going to move the electrons. This is also anti-clockwise direction of current. So, definitely this is also going to move the electrons in clockwise direction. You see, if the amount of electrons motions are reducing, it is not, EMF is not accepting it. EMF is supporting the electrons flow now. It always opposes the very cause of its production. Whatever the cause is there, if it is an increasing cause, it will not allow the increment. If it is a decreasing cause, it will not allow the decrement. Okay, so that is how the Lenz's law is going to be obeyed in every system. For every system, every system which works on Faraday's laws of electromagnetic induction has to satisfy Lenz's law. The best example I can tell you here it is, okay, father, mother, okay, here kid will be there, right? Kid is like an EMF. Kid is like an EMF. Father, mother is like a flux lines and conductor. Let me take up mother is a conductor. Or otherwise, you take up conductor, flux lines, anything is okay, fine. Whoever is going to start the fight, you see. If father starts fight with the mother, then kid will go and oppose father. If mother starts fighting with father, then kid will go and oppose mother. Alright, so kid is an EMF always opposes who is the reason for the production. Who is the reason for this fighting? If EMF is not there, what will happen? This fighting continues. Finally, one will win and divorce. Okay, so please, for the existence of this married life, kid must be there. Otherwise, it might lead to divorce also. The system will be imbalanced. Lenz's law has to be satisfied. Otherwise, system cannot survive. Okay, so this is about Lenz's law. All right, now let us move on to some problems we have got here. Okay, so the problems are like this. The problem he has given it as, the circuit shows a two-winding lossless transformer with no leakage flux, excited with a current source I of t, whose waveform is also shown. The transformer has a magnetizing inductance of 400 by pi millihenries. Now he is asking the peak voltage across A and B terminals with S open. S means switch over there in the diagram. So he has given, by the way, lossless transformer. Okay, so if you give current, it will drive a current and it will create no drop in the windings. So whatever the voltage which is available here, same voltage is also available here, 1:1 transformer. If I take up N1, if I take up N2, then E2 will be same as like E1. So if you want to calculate voltage across AB, then you calculate voltage across these turns, N1 turns. Voltage across N1 turns, voltage across N2 turns will be same. Why? The flux linkages with respect to N1 and N2 are same now. You can write E2 is equals to N2 into d phi by dt. You can also write E1 is equals to N1 into d phi by dt. Yes or no? This d phi by dt is common na. For the turns 1 and turns 2 both are common. So I can say that E2 by N2 is equals to E1 by N2 is equals to E1 by N1. So these ratios are same. So otherwise you can write it as E2 by E1 is equals to N2 by N1. As N2 by N1 is 1:1, I can say that E2 and E1 both are same. You calculate the voltage here or here, whether he is asking voltage across AB or voltage across first turns, anything is okay. How do you calculate now voltage across first turns? I have a current source here. The current into inductance of this coil. The current into inductance of this coil. But I have a formula in terms of EMF like this, N into d phi by dt, N into d phi by dt. This N into d phi by dt can be taken like this. N into d phi by dt can be taken like this. If you remember, N into d phi by dt can be taken like this. The change in flux lines are because of what? Change in current. So I am taking like this. I just multiplied and divide with di. So di can be cancelled, again the same formula, above formula. This N into d phi by di is called the inductance. If it is coil 1 inductance. If it is coil 2 inductance. If it is between the coils, it is mutual inductance or magnetizing inductance. Okay, he has mentioned it as magnetizing inductance. Chalo, take up the magnetizing inductance and change in current and you will get the EMF. He is expecting peak voltage across A and B. If you are expecting peak voltage across A and B, that means what? He is expecting this voltage as a large peak voltage. Then there must be change in current also should be maximum. If the change in current is maximum, EMF also going to be maximum. When will you get change in current as maximum? You see, look at the current waveform. So start from here and till the maximum point. If you take up till the maximum point, the change is from 0 to 5 millisecond, the change in current is maximum. So consider this 0 to 5 milliseconds and substitute there, you will get the answer. Okay, so if you know how to find the slope, right? y2 minus y1. What is the y? What is the magnitude of this? 10. So 10 comma 5 milli. By the way, time axis is milliseconds. Be careful. Do not forget. If you forget milli, gone case answer. Okay, and this is 0 comma 0. If you try to find out the slope, I am finding out the slope of this one. Let me find out the slope of this one as m. So m1 is equals to how much? y2 minus y1 by x2 minus x1. Oh, sorry, I have written in a ulta different manner. That is actually, I should write it as 5 milliseconds comma 10 milli. 10. So y2 minus y1 is 10 minus 0, x2 minus x1 is 5 milli minus 0. So I will be getting it as 2 kilo. I am getting the slope as 2 kilo. Or otherwise di by dt is equals to 2 kilo. You substitute here, you will get it. Substitute here, you will get it. How much? If I substitute, the EMF is equals to N is or L is how much? 400 by pi milli henries into di by dt, I2 minus I1 by T2 minus T1. I2 is 10 amperes, I1 is 0 amperes. So 10 minus 0 divided by T2 is 5 milliseconds, T1 is 0 seconds. We did already 2 kilo. 10 by 5, you'll again get 2. If milli goes up, 2 kilo. So otherwise kilo milli gets cancelled. Now 4000 by pi, otherwise 5 eighths probably, 800. If you do this calculation, 800 by pi volts. C could be the correct answer. You see, the current wave is an alternating wave. That's the reason why transformer is able to generate the EMF. If the current wave is a constant wave, EMF is 0. Where till how much duration the wave is constant, till that much duration EMF is 0. You remember that point. Because according to waveforms also they'll ask. Now one more question he has asked, the same continuous, same data. If the current waveform is 10 sine 100 pi t amperes, the peak voltage across A and B with switch closed. If I close the switch, what will be the voltage? This is 1:1. I have A terminal. Now if I close the switch, I have a resistor, some value, and he is asking if the switch is closed and this current source is now sinusoidal. Again the same formula, na? He is asking voltage across AB, whether it is voltage across AB, whether it is voltage across N1 turns, whether it is voltage across N2 turns, it will be same because it is a 1:1 transformer. So voltage across AB or voltage across N1, N2, all are same. So L into magnetizing inductance into di by dt. What is the magnetizing inductance? 400 by pi millihenries into differentiation of current waveform. If you differentiate it 10 sine 100 pi t, if you differentiate it 10 into differentiation of sine will be cos 100 pi t into 100 pi. Okay, into 100 pi. So pi can be cancelled. Now this is milli, this 10 and 2 zeros can be cancelled. Now we are getting it as 400 into cos 100 pi t. 400 into cos 100 pi t. This is not a maximum voltage. This is an instantaneous voltage. Instantaneous voltage. What is this maximum voltage now? If the instantaneous voltage is looking like this, then this is the maximum voltage. Peak voltage is this one, na? Peak voltage is this one. So if you look at this one, option A is the correct answer. Okay, I hope it is clear for you. Now let us do one more question. This is a very good question. So please try to understand here. There is a small correction to be done. The winding is like this actually. The winding is given actually like this. Now it will be drawn like this. Okay, like this. You see, same as the sense of the first winding and second winding. He is asking a question. The core of a two winding transformer is subjected to a magnetic flux variation as indicated in the figure. Here is a core. This core is subjected to a magnetic flux variation as indicated in the figure. The figure is missed here. Let me draw the figure here also. The flux variation is given like this. Time in seconds, 0, maybe 1, 2, 2.5. 0 to 1, it is a ramp signal. 1 to 2, it is a constant symbol. 2 to 2.5, again it is a ramp. Now the peak of this is going to be 0.12 Webers. The flux is in Webers. The flux axis, y-axis is flux axis and the units are Webers. X-axis is time axis and the units are seconds. If this kind of waveform is given and that kind of waveform is establishing in the core, no doubt EMF will induce. What he is asking? What he is asking? He is asking the induced EMF in the secondary winding as a function of time will be. The induced EMF in the secondary winding, not in this winding he is asking. We know the flux, so d phi by dt into N2. D phi by dt into N2 na. So induced EMF is going to be N2 into d phi by dt. Now N2 I know 200. N2 I know 200. Okay. Into d phi by dt. The change in flux you need to calculate. You see the change from 0 to 1. If you take up 0 to 1 duration, 0 to 1 second duration, the change is phi 2 minus phi 1, 0.12 minus 0 divided by 1 minus 0. So I can write it as 0.12 minus 0 divided by 1 minus 0. If I will be getting this one as 200 into 0.12, we will be getting it as 24 volts. Similarly, if you can do it for 1 to 2 duration, can you tell me? The 1 to 2 duration, the flux is constant. There is no change. If there is no change, phi 2 is 0.12, phi 1 is also 0.12. T2 is 2, T1 is 1. Even though the time is changing, the flux is not changing. D phi is 0. The change in flux is 0. If the change in flux is 0, the EMF is 0. You see the waveform. During 1 to 2 duration, EMF is 0. During 1 to 2 duration, EMF is 0. In all the options, 1 to 2 duration, EMF is 0. It is clear because during that time, EMF is, the flux is constant. It is like a DC waveform. Transformer action is not possible. EMF induction is not possible for DC supplies. Or during that duration, if the waveform is constant for certain time, during that time EMF induction is not possible. So I can write 1 to 2 duration, 1 to 2 seconds, EMF induced in the secondary is going to be 0 volts. No need to write anything. Now 2 to 2.5 duration, the EMF can be taken as N2 is 200 and d phi 2 minus phi 1. Phi 2 is going to be what? 0, no. Phi 1 is what? 0.12. Now x2 minus x1, y2 minus y1 divided by x2 minus x1. What is the x2 time axis? 2.5. x1, 2. So if you solve this one, minus 0.12 divided by 0.5, it comes out as minus 0.24 into 200. We will be getting it as minus 48 volts. You see, first 1 to 2, 24. 0 to 1, 24, 1 to 2, 0 and 2 to 2.5 minus 48. This option, this waveform is satisfying. Remaining options are not satisfying. This we have got it as ulta. Be careful, people will go ahead with this one. No. The polarity of induced EMF has to be here, it matters. If you take negative minus n into d phi by dt, you will be getting it as B option. No. When to take negative, when to take positive is very, very important. If lens law is satisfied, don't take negative sign. If lens law is not satisfied, then take negative sign. Okay. If EMF is opposing the source voltage, if EMF is opposing the source voltage, lens law is satisfied. Don't take the negative polarity. That means what? EMF polarity should be same as supply voltage. Okay, you can write if EMF is not opposing the source voltage, then take the opposite polarity, negative polarity. So be careful. All right. So these are some questions on induced EMF. Okay, we will move on to probably the construction of the transformer. Before moving on to the construction of the transformer, we will be discussing about one more question. This is a very good, very good question. Please try to understand, and then we'll move on to the construction of the transformer. If you look at the question, consider one turn rectangular loop of wire. One turn rectangular loop of wire is placed in a uniform magnetic field as shown in the figure. The plane of the loop is perpendicular to the field lines. The resistance of the loop is 0.4 ohms and its inductance is negligible. The magnetic flux density is a function of time is given as 0.25 sin omega t, whereas omega is 100 pi radians per second. The power absorbed by the loop from the magnetic field is, you see the figure is like this. This is a rectangular loop, one turn rectangular loop. If I take up this as a rectangular loop, now for this rectangular loop plane, the flux lines are perpendicular like this. The flux lines are perpendicular like this. This is a perpendicular flux line. Okay, right. And the flux lines are changing, time varying. Conductor is stationary, flux lines are time varying. Therefore, EMF inducers are not. No doubt EMF inducers. By the way, he said that it is a loop. If it is a loop, definitely current flows or not. Definitely current flows or not. No doubt the current flows. If the current flows, power dissipation takes place. That is what is asking, power dissipation. Okay. So EMF can be taken as here N into d phi by dt. Rate of change of flux linkages will induce an EMF. How it is changing? Though it is perpendicular, it like this. Okay, like 1 flux line, 2 flux line, 3 flux line, 4 flux line and 5 flux line like this. Again 5, 4, 3, 2, 1 like that. You can know like this. If this is a plane, if you are the plane, 1 flux line, 2 flux line, 3 flux line, 4 flux line and 5 flux lines, all are perpendicular. Okay, and again later 5 to 4, 4 to 3, 3 to 2, 3 to 1 and 0 and it becomes. So they are perpendicular, they are changing with respect to time, so EMF definitely induces. Okay, now you need to calculate the change in flux here. We know turns, number of turns is just, he has given it as 1. How to calculate the flux here? We know flux density he has given. If he has given flux density is equals to flux per area. So flux is equals to B of t or B into A. Let us take up the B. How much is the B? 0.25 into sin omega t. Omega I am substituting 100 pi into area. What is the area? He has given the dimensions 5 centimeters into 10 centimeters. 5 into 10, 50, 50 into centimeter square. So it will be 50 into 10 to the power of minus 2 whole square. 10 to the power of minus 4 you will get. You substitute, you take up this flux and substitute in the EMF equation. Okay, you will be getting it as, you will be getting the EMF as 1 turn into d phi d by dt of 0.25 into sin 100 pi t. Of course area is there, no? Okay, let me take up the area as 50 into 10 to the power of minus 4. Okay, this constant term is there. You can any other term is missing. 0.25 into sin 100 pi t. That's it. Okay, so 10 to the power of minus 2 whole square is going to be 10 to the power of minus 4. If you solve it, 50 into 0.25 into 10 to the power of minus 4, and of course if you differentiate it, so this constant will be, I am getting it as around 1.25 into 10 to the power of minus 3. If you differentiate it, differentiation of sine is cos 100 pi t into 100 pi. So multiply this 1.25 with 100 pi. I am getting it as around 0.392 into cos 100 pi t. This is the induced EMF. But I want power, na? Power can be taken as I square into R, or otherwise V square by R. I don't know current. I know the voltage. You directly substitute in this one. By the way, these are RMS voltages, RMS currents. So be careful. Here we have an instantaneous voltage. We have a maximum voltage. This is a maximum voltage, not RMS voltage. So please convert into RMS and then calculate. RMS value will be maximum value by root 2 whole square divided by resistance is of 0.4. Okay, so you'll be getting it as 0.392 divided by root 2 square of it divided by root 2 square of it and divided by 0.4. I am getting the value as around 0.192 watts. This is the power consumption by the rectangular loop of wire. Okay, so these kind of questions are asked in gate examination. These questions are asked in gate examination. Okay, so you see, please try to practice as many problems as possible, and we will discuss about the core construction. Okay, the next session.